Welcome back to this video series on trees and tree-based data structures. In this part we develop heaps, which are binary tree-based data structures that offer guaranteed efficient operations. A heap, or more specifically a max heap, is a binary tree of depth d that satisfies the following three properties. First, the binary tree is full up to level d minus 1. That is, every node at every level is present from the root level through the second to last level. At the last level, the heap is full to the left, meaning that the nodes are as far left as possible and there are no gaps. The final property is that every node has a key value that is greater than both of its children. The first two conditions together are known as the fullness property, because the tree is full or complete except for possibly the last level, but which is full to the left. The third condition is known as the heap property and provides a different structure on node keys than binary search trees. Here's an example. From the root level to the depth 3, every node and every child is present. At the deepest level, we only have two nodes, but their position is all the way to the left. Moreover, the key of every node is larger than both of its children. We call these data structures heaps because graphically they represent a pile. Ultimately, we'll be adding elements to the heap, but like throwing something on top of a pile, we will not necessarily have control on where it ends up in the heap. It is important to understand that heaps are not binary search trees. As a consequence, they are not general-purpose collection data structures like binary search trees are. We cannot effectively search, insert, and delete nodes in a heap. However, heaps have their own interesting properties and efficient operations that make them well-suited for other applications. As before, we'll require that our keys be unique, non-negative integers. These conditions can be relaxed or made irrelevant through the use of comparators. Because of the heap property, a max heap will always have its largest key value at the top of the heap. Because of the fullness property, we have a guarantee that the depth of the heap will be logarithmic. These are the properties that we're going to exploit to develop an efficient data structure and operations. Equivalently, you could define a heap to be a min heap in which both children are greater than their parent. In a min heap, the minimum key would be at the top of the heap. Here's an example of a min heap with the same fullness structure. Though you can alter the definition, two implementations are actually not necessary in general. In practice, you would use a comparator to determine the relative ordering of keys, and so a min heap could be created from a max heap implementation by using a comparator that reversed the ordering. Another important observation is that though the extremal element, that is the min or the max, will always be at the top of the heap, we cannot definitively say where other elements are located. For example, in this heap, the maximum element could be at the last level or the second to last level, but we would have to do a full tree traversal to actually find it. In fact, any search for a particular element in the heap would necessarily involve a linear tree traversal algorithm. This limitation is what makes heaps inappropriate for general-purpose collection data structures. Nevertheless, we can identify two core operations that do make heaps extremely useful. The first operation is a getMax operation that retrieves and generally removes the element at the top of the heap, the maximal element. The second operation is a general insert key operation. Both of these operations will be efficient because of the fullness property, but since we limit our data structure to these two core operations, it's a restricted access data structure similar to stacks and queues. As we develop both operations, we'll need to ensure that we preserve the heap property as well as the fullness property. Both operations will need to be proportional to the depth of the heap to guarantee that they're logarithmic. As alluded to before, insertion is not going to be arbitrary. That is, we cannot simply insert a node anywhere we like because we have to preserve the fullness property. You could design a heap data structure to support other general methods, but they'll not necessarily be efficient. Arbitrary retrieve or remove, for example, would be linear, as you may need to search the entire tree to find the node or place to insert. The first operation that we'll develop is the insert key operation. Again, we need to preserve both properties. However, heaps are not binary search trees. We cannot use the same approaches with them. To illustrate this, consider the following attempt at inserting a new node 100 into the following max heap. The naive approach would be to treat it like a binary search tree and start at the root. Since 100 is larger than the root, it needs to become the new root, and so we shove 95 down further in the tree. In this case, we've chosen to move it down to the child with a smaller key value. That pushes 45 further down the tree, which pushes 15 down to a new leaf node. But this is no longer a heap, as the fullness property is violated. There's a gap under 72. This process still wouldn't work if we pushed the larger of the two children, as we could easily come up with another counterexample that ends up with a gap. The solution is to take a different approach and make it our priority to preserve the fullness property. Instead of starting at the root like we've been doing with all binary trees, we'll start at the bottom and insert a new node at the bottom. We'll insert it at the deepest level, the leftmost available spot. We may need to start a new level if the last level is full. Here's the correct insertion operation. We insert 100 at the deepest level all the way to the left. The fullness property is now preserved, but the heap property may no longer be satisfied. We need to fix the heap so that it is. This process is generally referred to as Heapify. It involves exchanging key values up the tree until the heap property is satisfied or we reach the root. Here's the heap from before. Since 100 and its parent are out of order, we swap them. The heap property is still not satisfied, as 193 are out of order, so we swap them again. And now 195 are out of order, so we make one last swap. And 100 becomes the new root key. The heap is now fixed and both properties are satisfied. Here's the pseudocode to Heapify from the bottom of a heap to its top. We start at the newly inserted node, and while we've not made it to the new root, and it's out of order with its parent key, we swap the keys and move up the heap to its parent. The analysis is pretty straightforward. First, we'll assume that we have free access to the next available spot in the heap. We'll revisit this assumption in detail later on, but for now we'll treat it as a constant operation. The heapification process can, in the worst case, be proportional to the depth of the heap. However, the fullness property guarantees that this will be logarithmic with respect to the number of keys. This analysis is the same whether you consider key comparisons or swaps to be your elementary operation. The other operation is the getMax operation. The heap property here helps us, as the maximum value is always guaranteed to be at the root. As a variation on this, we could support a peak-max operation that retrieves but does not remove the root element. Otherwise, by default, the getMax operation generally removes and returns the maximum element. However, we have the same problem here as before. Removing the root element leaves a gap in the heap that we need to fix. If we take the same naive approach as before, starting at the root, we'll remove the key and save it off to return it. To preserve the heap property, we could promote the larger of the two children, in this case 93. That results in another gap, and so we promote 72. However, again, this leaves a gap in the heap with no further children to promote up. The correct getMax operation would, as before, first ensure that the fullness property is preserved. Thus we'll replace the root with the last element. The last element is the rightmost element at the deepest level of the heap. Once we've made the swap, we'll heapify to fix the heap, but in this case we do it downward instead of upward. Here's the example again. We've already removed the root element, so we replace it with the last node, 53, whose node is then removed. The heap property is violated, so we swap with the larger of the two of its children. The heap property is still violated, so we swap with the larger of its two children. And now the heap has been fixed and both properties are satisfied. The complexity is the same as with insertion. Again, we'll assume that we have free access to the last element of the heap. Swapping the last and the root are constant operations. However, swapping the new root with its descendants will be proportional up to the depth of the tree. We may get lucky and not have to move the new node all the way down the tree, but in the worst case, it would give us order D operations for both comparisons and swaps. We leave the pseudocode as an exercise. However, we will go through the details of how to implement a heap and create a simple Java implementation. To make our lives simpler, we'll leverage other data structures and use composition to design our heap. We could implement a heap using a binary tree and binary tree nodes. However, the simpler implementation is to use an array. Since the binary tree in a heap is full, all of its data can be stored contiguously. This suggests that we can use a traditional array or array-based list to store our nodes and node references. The way that this works is that we store the root at index 1. Now, in general, if a node u is stored at index I, then we can easily compute the indices of its children and even its parent. The left child will be stored at index 2 times I, and the right child just one cell over at 2 times I plus 1. Reversing these formulas gives us the parent at I divided by 2 taking the floor. This scheme ignores the cell at index 0, but you can easily modify it by subtracting 1. Here are the nodes and their corresponding indices illustrated graphically. And here's the heap example that we've been using to store an array. There are no gaps in the heap, and so there are no gaps in our array. Traversing to the children and to the parent are now simple index evaluations. If you observe carefully, you'll notice that the elements are stored in the array in a BFS ordering of the tree. Reading the heap elements left to right, top to bottom, gives us the ordering in the array. Using an array to implement a heap has several advantages. First, it's a familiar, simple, and easy data structure to use. Note that we would not be able to use a linked list for a heap implementation, as the lack of random access means that we would not be able to retrieve the elements in constant time. Also, the fullness property guarantees that the data is contiguous, so it would not be a good idea to implement a general binary tree or binary search tree with an array, as there would be large, potentially exponentially sized gaps of wasted memory. It also solves one of the issues that we mentioned before. We had assumed that we had free access to the last node as well as to the next available spot to insert elements into the heap. With an array-based implementation, this truly becomes a constant time operation if we keep track of the size of the heap. The last element will always be at index n, and the next free available spot will be one right after that. Though an array-based implementation is generally preferred, it is possible to use a tree-based implementation using tree nodes and a root reference. The issue is that without random access, we don't have free, constant time access to the last node or the next available spot. It is still possible, however, to find these two positions in the heap without impacting the performance of the two operations. Specifically, we can find the positions in order log n, matching the complexity of the Heapify processes. We won't present all of the details here, but we will sketch an outline of how to find the next available spot. The operation for finding the last node is similar. First, we keep track of n, the number of nodes in the heap. This allows us to compute the depth because of the fullness property. Now, starting at the root, we need to determine, is the next available spot in the root's left subtree or the right subtree? To answer that question, we just need to do a little arithmetic. First, we can compute the number of nodes in the heap from the root level to d minus 1, using a well-known geometric series formula. This in turn tells us how many nodes are present at the last, deepest level, level d. If the last level were full, there would be 2 to the d nodes. Since it's a binary tree, they would be evenly split between the left and right, so that each part would have at most 2 to the d divided by 2 nodes. Since we know how many nodes there actually are, we can make a simple comparison to determine if the left subtree is full at level d or not. This tells us if the next available spot is in the left subtree or the right subtree. We can then traverse left or right and repeat the same calculations until we get down to the node with one open spot. Since there are a constant number of operations at each level, the complexity is order d, which is order log n. Though it is possible to implement a heap with a tree data structure without ruining the theoretical complexity, the implementation itself is more complex and requires more operations. Let's now design and implement a max heap for integers in Java. We'll make our lives simpler by using an array list as the underlying data structure. We'll implement both core operations of insert and getMax. First, we need our underlying array. And we'll need a constructor. We'll add a dummy variable to index 0 so that we can use the indexing scheme that we described. Let's write some convenience methods. We subtract 1 to make up for that dummy variable at index 0. Now let's write the insert method. start at the last element that we just inserted. We've translated the conditions here in terms of our array. I not being the root is equivalent to I being greater than 1. The comparison checks to see if the keys are out of order, relying on truncation to do our floor operation. Moving up in the tree is another division and truncation operation. Now let's implement the getMax method. Let's take care of some corner cases first. If the heap is empty, we'll go ahead and throw an exception. As another corner case, if there's only one element in the heap, we simply remove it without any heapification. Otherwise, we'll get the max and save it off to a temporary variable to return it later. Now let's replace the root with the last element. And heapify downward. We'll exchange the node with the larger of its two children, so we need to determine which one it is. If only the left child exists, we have no choice. If neither child exists, then we've reached the end of the tree, and so we stop the process. And we traverse down to the node that we just swapped. Finally, I'll add a toString method so that we can observe the contents of the array as we're testing. Let's write a quick test. These numbers are from our example. This isn't that rigorous of a test since we're inserting them in the same BFS order, meaning that no heapification will occur, but at least it gives us reason to believe that we didn't make a mistake. Though heaps are restricted access data structures, they nevertheless still have many useful applications. Heaps are used in many algorithms to store elements so that they can be processed in order. We'll examine two immediate applications, priority queues and sorting. Recall that when we discussed queues, one variation was a priority queue. Elements may be inserted arbitrarily into a priority queue, but when removed, the next element out of the queue is the one with the highest priority rather than a FIFO ordering. Heaps provide exactly these operations, but in an efficient order log n manner. Another application is sorting. Given n elements, we simply insert them into a min or max heap one by one, and then remove them one by one. The order in which they're removed results in a sorted collection. Since each insert and remove is at most order log n, and there are most n iterations, the overall complexity to use a heap to sort is only order n log n, theoretically matching other fast sorting algorithms such as merge sort, quick sort, and tim sort. Let's implement this idea in Java. This method will take a list and create a new list that represents the same elements but sorted. Extremely simple code. We simply put each element in and then take each element out. Let's test it. And it works. This is a quintessential example of one of our themes, that smart data structures and dumb code are a lot better than the other way around. Heap sort represents dumb code, put stuff in, take stuff out. The real magic occurs within the data structure itself, and we exploit its properties and efficiencies to solve another problem.